All right, we're going to start our study of circular motion. I'm going to start off with an example. A car is traveling at a constant speed of 20 meters per second in a circle with a radius of 40 meters. Is the car accelerating? And at first glance, you might say, oh, it's going constant speed, therefore it's not accelerating. However, that's not the case. If you remember, acceleration is change in velocity and velocity is a vector. So it can happen three ways. It can slow down. That's one way of changing velocity. It can speed up, or you can change direction. So in changing direction, you're changing the velocity, so you're accelerating. So the answer is yes, you are accelerating because you are changing direction. So don't let that fool you. Now, the direction of the velocity, the acceleration, and the force. So I'm going to draw this car, okay? And let's say the car is going on a road that's curved like this. This is going to be a top view. So I'm looking down at the top of the car. So there's the car, and here are its wheels, like so. Now, the velocity is the direction it's going at that moment. So the velocity is going to be off this way. All right? Now, the acceleration is in towards the center of the circle. I'm going to put a C there, and I'll explain what that means in a minute. And then the force is also going to be towards the center of the circle because F equals ma, so force is mass times acceleration. The force and the acceleration have to be in the same direction. So we're going to say that the velocity is a tangent to the circle. And the acceleration and force are centripetal. Okay, that is what the little C stands for in here in FC and AC, which means toward the center. Excuse me. So you may be asked to draw a picture like this. This is not a free body diagram. In a free body diagram, you only put the forces. In this case, I'm putting V and I'm putting acceleration on there as well. So just know how to draw that. Okay, and know how to draw free body diagrams. We'll do free body diagrams with these problems later on. The equations for this, the acceleration is equal to v squared over r, where v is velocity, r is the radius of the circle, or the radius of the turn. And if I combine that with F equals ma, I end up with this. Okay? F equals mv squared over r. The nice thing about circles is when you see a circle problem, you almost always know you're going to use this equation for the acceleration. Now, for some examples, what's the acceleration of the car in the example above? In the example above, we have a velocity of 20, speed of 20, and a radius of 40. So we'll write those down as our given. Velocity is 20 meters per second. Radius is 40 meters. And we'll do A is v squared over r. That's 20 squared over 40. And if you evaluate that, you end up with 10 meters per second squared for the acceleration. The units are going to be the same as in the Archimedes one-dimensional motion unit. So acceleration is going to mean meters per second squared. Next example, a fighter pilot can withstand an acceleration of 8 Gs before passing out. You may have heard that term, 5 Gs, 8 Gs, 6 Gs. And for human beings, if we get too high of an acceleration, too many Gs, you're going to pass out. For people, it's usually around 5 Gs. Fighter pilots train so they can withstand more, maybe up to 8 or 9 or 10 Gs. But eventually, if they get a big enough acceleration, they're going to pass out. And that's kind of bad if you're flying a plane. So, and the plane is traveling at 500, and we want to know the minimum radius, because the smaller the radius he turns in, the greater the acceleration is going to be. So, the acceleration, we said, is 8 g's. When you hear that, 8 g's, it means 8 times the acceleration of gravity. So that means 8 times 10. So it's going to be 80 meters per second squared. The velocity is 500 meters per second, which is not unreasonable for a fighter jet. And then I want to know the radius. So A equals v squared over r. I'm going to do some rearranging here. If I cross multiply it, I'd get a times r equals v squared, and then divide by the a, and I get r equals v squared over a. So that gives me 500 squared over 80. 500 squared is going to be 25 and then 4 zeros, so 250,000. And we're going to divide that by 80, and we're going to get a radius of 3125 meters. So if he tries to go in a circle with a smaller radius than that, you will pass out. One more example at the top of the next page. Now, we have a roller coaster with a vertical loop in it. It has a height of 20 meters. It gives you the mass of the roller coaster. And this is where we might have to draw a free body diagram. So we'll start with that. I'll put it up here, actually, A. This is a little bit of a tricky free body diagram. I'll draw my little roller coaster car. Now, one force that's on it is going to be pretty obvious, is the force of gravity. That's going to point down. So Fg. And if the mass of this is 100, we know that force of gravity is going to be 1,000 newtons. Now, this might be a little surprising, is which way the normal force is pointing. But right here, the track is above the car, so the track is pushing down on it. So the normal force is actually down, like that. Now, if we ignore friction, there are no other forces acting on it, and that is our complete free body diagram. Now, you'll notice I haven't drawn an FC on there. You never do, okay? You have to actually be able to think physically of what the force is. So there's going to be gravity, there could be normal force, there could be tension, there could be friction, but centripetal force is not is always the F net, made up of forces that we can point to. Part B, write an equation of motion, an F net equation for the car. Okay, so Fn and Fg are in the same direction. If they're in the same direction, I'm going to add them. So when I do my F net equals Ma. Okay, then that's going to be Fn plus Fg equals Ma. Now, we can go farther with that. We could either do it here in part B or move into part C. So I'm going to box this in, and then I'm going to show you what you do from there. Okay, now, we can write Fn. Now, our Fg is 1,000 equals, our M was 100. And what we can do for A, since it's going in a circle, anytime something's going in a circle, I know I can write V squared over R for that. Okay, now we've actually kind of started part C. We want to find the minimum speed in order for it to remain in contact with the track. Okay, now, the trick to this, okay, is the minimum speed occurs when Fn equals 0. So if you think about this cart's going around this track up here like so, right? And the faster it goes, the harder it's pushing up into the track, and the harder the track pushes down on it. So the faster it goes, the bigger the Fn is going to be. As it slows down, the Fn will get smaller and smaller until right at the very top it loses contact with the track. Okay, and that's the slowest I can go and make it around the circle. If I go slower than that, I might lose contact earlier back here, and then it would fall off. So if I want to find the minimum speed, I'm going to set Fn equal to 0. So going back to our equation here, we're going to get 0 plus 1,000 equals 100. We're looking for V, and the radius of this thing, if I go back up to the picture, the whole height was 20, so the radius would be half of that, or 10. So over 10. Now if I cross multiply, I get 10,000 equals 100 v squared. Divide by 100, and that gives me 100 equals v squared, and then v is going to be 10 meters per second. So as long as we go 10 or faster, we're going to be safe and stay on the track. If we go slower than that, it's going to fall off the track. Now, draw a free body diagram for the cart at the bottom of the loop. So we have, here's our cart. When it's at the bottom of the loop, we still have gravity down. Still 1,000 newtons. We'll write here that the mass is 100 kilograms. Now, when it's at the bottom and the track is down here, all right, the normal force is going to be upward. But I'm not going to say that it's going to be 1,000, because with 1,000, the cart would go straight. It wouldn't go up. If it was here and the two forces balanced, it would end up going straight this way. All right? So I have to figure out what the Fn is going to be, and that's what part F is going to be. So for part E, write an Fnet equation. Now, Fn and Fg are in opposite directions. I can do Fn minus Fg or Fg minus Fn. Now, what I want to make a note of here is that the Fnet for a circle remember, has to be centripetal or toward the center. And that's how we figure out whether it should be Fn minus Fg or Fg minus Fn. Since Fn is pointing towards the center of the circle, it has to be winning because our net force has to be towards the center. So when we do Fnet equals Ma, it's going to be Fn minus Fg equals m. Since it's going in a circle, we're going to change the A into v squared over r. And that's going to be our Fnet equation. Now in part F, we're being asked to find that normal force if it's going at the same speed. So Fn minus our Fg is 1,000 equals 100. We said it's going to be the same speed, which is 10, over r, which was 10. And then when we solve, we will get Fn equals, oh, I knew that didn't look right. I forgot the square over here. Okay, so this is squared. And then if we solve that, we'll get Fn equals 2,000 newtons. So if you take a roller coaster, when you get to the bottom of the loop, you actually feel heavy because the normal force on you, which is kind of what feels like your weight, is actually double, in this case, double what the force of gravity is.